Well, good afternoon, everyone, and welcome to today's live astronomy program, helping you see outer space without leaving your place. My name is Justin, one of the astronomers at the Science Museum of Virginia, and as always, I'm happy to bring a little bit of the dome into your home. All right, that's enough rhyming for today. Of course, as always, also happy to thank our sponsor, Allianz Partners. The series wouldn't be possible without them. And if you are willing and able to help the museum out in these times, we'll have some links for you in the comments as well. If you've watched some of the previous episodes, welcome back. Hope you're enjoying your journey to the edge of the universe. And if you're just tuning in for the first time, that's great. Just know that we are on an ongoing journey to the edge of the observable universe. And we won't see everything today. If you want to watch old episodes, they are archived here on our Facebook page. And then tune in again next week and we'll have another episode for you. For the rest of the show, I'll be showing you video created by the same software that runs the Dome Theater at the museum. It's planetarium software called Digistar 6, and it can do some pretty cool stuff. So you may catch me at times looking over at a second monitor that I have set up to watch it. If you're able to watch this video on a large monitor, expand it to full screen, especially for this episode, it'll help you with a couple of things. So I encourage that. In fact, I'm going to switch you over to the view from Digistar right now. And before we really dive into this week's show, I do want to answer one question that I saw in the comments from last week. If you have questions throughout this show, feel free to leave them in the comments. May be able to answer some of them during this show or return to them next week. And the question that I saw was from Shannon, who asks, have we tried to send different types of signals out to reach alien life, assuming aliens may communicate and or sense their environment differently than we do? Well, the short answer is no, not really. There have been a couple of different modes that we have tried to communicate with aliens. For example, you got the famous golden record that went out on the Voyager spacecraft. There were two Pioneer spacecraft launched in the 70s that had small plaques on them as well. And there are radio signals like the Arecibo message that I talked about last week. But ultimately, all of those messages require anyone that might receive them to be able to decode the pictures or audio that we send. So although they take a few different forms, a lot of what we broadcast is kind of similar. We do sometimes look for civilizations that might be using different methods. Like some scientists want to use what's called optical SETI, where they search for maybe giant laser beams that other civilizations might be shooting across the galaxy. That's something we can't do, but it's something that's someone to look for. And sometimes our audio messages are just a little bit different. For example, back in 2001, a Russian team sent a theremin concert out across the galaxy. Maybe that's why the aliens haven't answered us yet. So that's our effort to communicate with other intelligent civilizations. For now, though, I want to focus on some things a little bit closer to home and start with some current events. You may have seen some headlines about a comet that is now visible in Earth's skies. If you're an early riser, get outside in the last 90 to 60 minutes before the sun rises and look towards the northeastern horizon. That's where you should be able to find a comet called C2020F3. Or Comet Neowise. Now, if you go a little bit closer to sunset, more like 5 a.m. here in Richmond, it's about 1 hour before the sun rises, the comet will be a little bit higher in the sky, and the sky will still be dark enough that you should be able to pick it out. To help you out, the brightest planet in our nighttime sky, Venus, along with a relatively bright star named Capella, will kind of be in this quadrant of the sky to help you locate the right patch. Now, it is technically a naked eye object. You don't need binoculars or a telescope to see it, and although I haven't seen it with my own eyes just yet, I do hear that binoculars will certainly help you locate it quite a lot. If you've seen any cool pictures of the comet online recently, just know that a lot of those are long exposures, a few seconds at least, so it's not going to look quite as bright and detailed to your own eyes as it will to a camera. And if, like me, you're not an early riser, just hope that the comet stays bright for the next week or so, because by this time next week, it will be appearing in the early evening skies, just after the sun sets. So that may give you a nice chance to see it as well. Comets are kind of a unique thing to see in the sky. It's not every day that there's one you can see with your unaided eye. We've had a couple of other comets this year that we thought would brighten the way Neowise has, but they kind of fizzled out. Comets are unpredictable that way. But we do now have a comet that can be seen, so I recommend trying to take a look at it if you can. Humans have been watching comets in the sky for thousands of years. And, many millennia ago, they were seen as unpredictable omens that appeared in the sky without warning. And it is kind of hard to predict what comets are going to do. And you can never really predict when you're going to see one. Take, for example, this comet here that we're able to observe right now. Let's back away from the Earth here. You get the familiar orbits of the planets there on the screen, and that long oval is the elliptical orbit of comet Neowise. You can see just how far it travels from the sun. The comet's orbit takes it roughly 7,000 years to complete. So if Neowise has ever visited the inner solar system before, there are no written records of it, because humans didn't invent writing until about 5,000 or 6,000 years ago. So that's kind of a surprising fact about comets, I suppose. Taking care of that early in the show this week. But we have been watching comets for thousands of years. And of course, astronomers, all the way back to the ancient Greeks and even before, were able to track comets and the sun, moon, and stars across the sky. And then there was one other familiar feature in the nighttime sky for those ancient astronomers, our galaxy, the Milky Way. Now, you might just be able to see it across your screen there. I'll try and make it a little bit easier to pick out here. Even today, if you get out in a nice dark part of the country, especially here in these summertime months, you might be able to see the Milky Way stretching across the sky. It's kind of a fuzzy band of light that you can see. Hopefully it's brightening up just above my video for you right up there. And you'll be able to see it on across your screen here. Now, people have been trying to figure out exactly what the Milky Way was for quite some time. You go back to those ancient Greeks, and they certainly have some colorful mythologies about why the Milky Way is there. As for scientific explanations, well, you could look back to perhaps Aristotle, who suggested that maybe the Milky Way was composed of some kind of emanation, some fire, some gas, being released from the stars that interacted with the Earth's atmosphere and made it glow. That's certainly not the case, but, we had a lot of things wrong in astronomy a long time ago. That's all right. Science is always evolving and building on itself. We've learned a little bit more about the galaxy, especially in the last 400 years. When telescopes hit the scene, astronomers were able to see the Milky Way in a little more detail and try and figure out what it was. Instead of some strange, mysterious glow, they just saw a lot of stars. So that gave a little bit of a hint about what the Milky Way was. Efforts to map the Milky Way date back hundreds of years. You can look back to the late 1700s. The astronomer William Herschel discovered Uranus, a whole bunch of comets. He tried to map the Milky Way as well by simply counting as many stars as he could. This is the map he produced. It's not all that accurate. You can see, hopefully, the sun there. It's kind of towards the middle of the map. It's just to the right of center. It's a little bit larger than the other stars that Herschel drew on his map. So that's the kind of map you get just from simply counting stars. And although it's not perfect, you can learn a few things with this technique. In fact, astronomers are still just counting stars in the sky to try and understand the Milky Way a little bit better. Of course, these days, that counting is a little more sophisticated. There's a spacecraft named Gaia It is a mission of the European Space Agency. It's been working for about 6 years now, simply observing the stars, as many as it can, and taking careful measurements of their positions, their brightnesses, their temperatures, their motions through space, allowing us to put together a little more complete map of the Milky Way. You're seeing a large number of stars were included in its most recent data release, some 1.7 billion individual sources. So about 1.7 billion stars that was able to map out in space. Now, the way they're spread out around us here, it doesn't look that different from a regular nighttime sky. It's just a lot more stars. You can still see it's a little bit brighter around the bright strip of the Milky Way we can see in our sky. And actually, if I get outside of this map as created by Gaia, you'll see that maybe it's not much more accurate than what William Herschel put together a couple hundred years ago. You just got a whole bunch of stars with the sun seemingly close to the center. But because Gaia is collecting much more detailed information about the positions and motions of these stars, and by the end of its data collection, it may be able to recreate much of the structure we think the Milky Way has and reveal those details to us. But for today's show, it wouldn't be all that much fun if I just gave you all the answers from one spacecraft. So we're not going to do that. We're going to leave Gaia behind here for just a second and recreate some of the other discoveries that astronomers had to make to help us better understand our galaxy. So let's rewind. Let's go back about 100 years. If you watched one of our recent Ask an Astronomer videos, we talked about how astronomers figured out that there were other galaxies outside of the Milky Way. I won't get into too much detail on that, but we'll drop a link for you in the comments if you haven't seen it already. One of the astronomers you'll meet in that video is named Harlow Shapley. Now, Shapley was really concerned with mapping the Milky Way as much as figuring out what those other galaxies were, and he suggested an interesting approach to understanding our galaxy. Instead of mapping all of the individual stars maybe we just focus on groups of stars, big clusters of stars like globular clusters. They get that name because these are big balls of stars. They are globe-shaped, so they are called globular clusters. And Shapley realized that you can see a lot more of them in the sky if you look off in one particular direction, generally towards the constellation Sagittarius. You can see a lot of them on your screen now, those much larger white dots. But if you're looking off in another direction, you aren't going to see nearly as many as those globular clusters. So if we scan around the sky here, we can find a place where basically none of those are visible. Oh, there's one more. That brightest other bright dot is the sun there. So Shapley thought, well, maybe these globular clusters are evenly spread around the Milky Way, and because they are not evenly spread around our sky, that must mean that the sun, our solar system, is not at the center of the galaxy. He was right about that, and he had a few other things wrong, but he was right that these globular clusters are evenly spread around the galaxy, and they can help us figure out our place in it. We're going to recreate some other discoveries here, and we'll do it step by step. So I'm going to leave those globular clusters there. I've added a line across our screen that shows kind of the midpoint of that bright band of light we can see in our sky. And there's a big yellow dot there to mark the sun's position. So this is the kind of map that Harlow Shapley was able to put together about 100 years ago. But it doesn't really answer many questions about what kind of galaxy we live in, how big it is, what shape it is. So it's still a little bit of a riddle to solve here. As astronomers started figuring out that there were other galaxies beyond the Milky Way, they started to notice that the galaxies came in two general types. There are spiral galaxies, which are shaped like spirals, and then there are elliptical galaxies, which you see on the right, which are just kind of big elliptical collections of stars. So we've got globe-shaped star clusters, spiral-shaped galaxies, elliptical-shaped galaxies as well. It makes it kind of easy to understand how astronomers are naming things out there, just going by shape. But let's see, if we just know where the globular clusters are in our galaxy, it doesn't really give us a whole lot of detail about the Milky Way, because both of these kinds of galaxies can have globular clusters in orbit around them. So we need some more clues. That star counting, like William Herschel and the Gaia spacecraft are doing, those aren't going to give us all the answers either. There's that same map of the stars from Gaia I showed you a moment ago, compared to the locations of these globular clusters. So that's not a complete picture, and that can't tell us everything that's going on. Maybe what we need to do, instead of counting all of the stars, is to count some specific kinds of stars. That's something that astronomers are doing today as well, and it's revealing some surprising features about our galaxy. One recent study focused on a kind of star that you'll also hear about in that Ask an Astronomer video. These are stars that helped us determine distances to other galaxies, and they're pretty useful for measuring distances in our own galaxy as well. These new colorful dots appearing on the screen mark the locations of something called Cepheid variable stars. Now, you can see that in close to the center of where we presume the Milky Way is, with all those globular clusters in the middle of your screen, and then extending out, say, just beyond the location of the sun. These Cepheid variables stay pretty close to that straight line going across your screen. So that suggests that maybe some major structures in the Milky Way are arranged in a thin, flat disk, which is pretty interesting and maybe points us more in the direction of us living in a spiral galaxy. But in this study, just published last year, the astronomers noticed something interesting. I'm going to freeze our position right about here. You can see that in the middle of your screen, all those Cepheid variable stars are lined up in a nice straight line, but especially towards the right-hand end, where it goes from green to yellow, the structure of the galaxy appears to kind of dip below the line there. That suggests that even if our galaxy is a thin, flat disk, it's not perfectly flat. It must be warped just a little bit at its edge. Astronomers now think that it is warped thanks to interactions with other galaxies, but that's probably a story for another episode. Let's rotate our view here just a little bit and look at the arrangement of these Cepheid variable stars from above, and you might be able to pick out some other interesting details. See, these stars are color-coded, and they're color-coded by age. The yellow ones are all about the same size as the same age as the sun, maybe a little bit younger. The green ones are younger still. The blue stars are even younger, and the purple ones are the youngest of all. And you can kind of see how the color appears to shift as we get closer and closer to the center of the galaxy. So that's hinting at some more interesting structures. But beyond this, it's going to be kind of hard to solve the puzzle of what our galaxy is like if we just use the light that our own eyes can see. Most humans can see a wide range of colors. You know the rainbow, from red to purple. That's the visible part of the electromagnetic spectrum. But the colors of light that the universe can use is much wider. Out beyond the red end of our rainbow that we can see, we've got infrared light and then long wavelengths like microwaves and radio waves. And if we were to extend our vision into the radio part of the spectrum, we could see even more about our galaxy. What I've got on the screen for you now are vast clouds of hydrogen gas. They're called H2 regions because the gas has been excited by recent star formation. I've got data from a couple of recent studies on the screen for you. There's some brighter orange clouds that are more on the right-hand side of your view, and then some dimmer yellow clouds that are more evenly distributed around the Milky Way. But I wanted to focus on those orange clouds because I think they're the ones that, to my eye, start to really reveal the structure of our galaxy. First, you might notice just to the left of the sun's position, that big yellow dot, there's a dark streak. and then it brightens up again. So there's a lot more clouds of these excited hydrogen gas a little bit closer to the center of our galaxy. Off to the right, it gets pretty bright just beyond the sun, then maybe a little darker again, and then brighter again. So I can almost start to pick out some stripes there, which I think is pretty interesting. And it's certainly not something that you would see in a bland elliptical galaxy. Those bands are signals that we must be living in a spiral galaxy. And indeed, astronomers have kind of connected the dots they've been able to see with mostly radio observations that stretch all the way across the galaxy and start to fill in the map of what our galaxy may look like from the outside. Now, we'll probably never see it like this from the outside, just because of the sheer scale involved. From side to side, this main starry disk of the Milky Way is some 120,000 light years across. So getting a picture like this would require some spacecraft that would have to travel at incredibly high speeds for hundreds of thousands of years. Pretty tall order. So this is kind of the best map we can build on our own. We've been able to figure out some other interesting things about our position in the galaxy as well. We're some 25,000 light years from the core of the galaxy, and the sun orbits the center of the galaxy every 225 million years or so. And that means the last time the sun was on this side of the Milky Way, dinosaurs were just getting their start on Earth, which I think is also a pretty surprising fact. Now, I'm just rotating our view of the camera here. A rotating galaxy wouldn't really look quite like this. See, you got to remember, this is just a huge collection of stars, perhaps 100 billion stars, maybe 400 billion stars. And each star has its own individual orbit around the center of the galaxy. It's those individual orbits that help give rise to things like that spiral structure that is so familiar in galaxies like ours. And these spiral arms may not be, or probably shouldn't be thought of as, say, solid structures that rotate with the galaxy like this. Here's a video from the European Southern Observatory that kind of illustrates what I'm talking about. Each individual star is on its own orbit, but there are places where the stars kind of get bunched up. Astronomers might call these density waves. If you've ever driven on I-95, you might just call it a traffic jam. You may not be stuck in a traffic jam all day, but it'll slow you down for a little bit. After you get through the traffic jam, other cars get slowed down. So the same kind of thing happens as stars orbit the center of the galaxy. They just kind of get bunched up every once in a while. That helps give rise to these arms, though I will admit that the formation of the arms isn't totally understood. As for the sun's own orbit around the galaxy, that reveals some interesting bits of information as well. I mentioned the time it takes for us to get all the way around the center of the galaxy, 225 million years or so. There's something else interesting that happens here. It's not just a flat circle or a flat oval that the sun moves in. I've exaggerated things quite a bit here, but the sun also rises above and dips below the plane of the galaxy. This cycle repeats several times per orbit. It goes about 33 million years between these galactic plane crossings, where we either move up through the plane of the galaxy or move down through the plane of the galaxy. There's actually been a lot of work to study whether these galactic plane crossings might be related to mass extinction events here on the Earth. I mean, there's one obvious example, those dinosaurs I mentioned a little bit ago. Their extinction dates to about 65 million years ago or so. That's about 2 of those 33 million year cycles. So maybe the sun was crossing the galactic plane at that time, maybe because it was in a more crowded part of the galaxy. The gravity from having more stars in the neighborhood helped dislodge asteroids and comets from their orbits, and that's what helped cause the collision that helped wipe out the dinosaurs. I don't know, it's an interesting idea, and the case certainly isn't closed on that, but it might be an interesting connection between our star's place in the galaxy as well as life here on Earth. So it's important to know our sun's place in the galaxy, what the galaxy is like. And even more recent work says maybe it's just we're in those galactic traffic jams when we're crossing through the spiral arms that we undergo those vast geologic changes here on Earth. So pretty interesting ideas related to our place in the galaxy. But if we're not at the center of the galaxy, what is? Well, hints about that were also revealed about 90 years ago by early radio astronomers. Now, they found a bright radio source also in the general direction of the constellation Sagittarius, where all those globular clusters can be found and where we know the center of our galaxy is. And that bright source was called Sagittarius A. And then when it was noticed that gas here was being excited, it was called Sagittarius A star. That's just an astronomy code. And in more recent decades, we've been able to track not just the radio emissions from the center of the galaxy, but also the motions of individual stars at the center of our galaxy. And just like the motions of planets, asteroids, and comets around the sun can be used to tell us fundamental things about our star, like the distance a planet is from the star and the time it takes for the planet to get around the star can tell us the mass of a star. Here at the center of the galaxy, the distances of these stars from the galactic core and the time it takes for them to orbit the core of our galaxy tell us that whatever is here at the heart of the Milky Way, whatever Sagittarius A star is, it's got to be really big. Its mass is something like 4 million times the mass of the sun. It's about the only thing that can be 4 million times the mass of the sun and also invisible to human eyes is going to be a black hole. This is what we would call a supermassive black hole, and we now think that almost all large galaxies like ours are built around a supermassive black hole like Sagittarius A star. Now, we've had to mostly measure it indirectly. Those radio emissions, the motions of these stars, things like that. We are working on getting a more direct image of the black hole at the center of our galaxy. You may remember a little over a year ago, a team operating a project called the Event Horizon Telescope released a picture of another supermassive black hole. This is one at the center of a galaxy called M87. The black hole is also nicknamed Povei after a name given by an astronomer at the University of Hawaii in honor of one of the telescopes that helped take the picture. What we're seeing here is also in radio light, and you see kind of the shadow of this supermassive black hole at the center of the image. And the glowing ring is just material in what's called an accretion disk, dust and gas in orbit around the black hole. As it interacts with the black hole's magnetic field, it also releases the radio waves that we're able to detect here. And it's brighter on one side because of the rotation of the black hole. There's a lot more information that can be gleaned from this image, and the Event Horizon Telescope is also working to produce a real image of our local supermassive black hole, Sagittarius A star. In the meantime, study of the center of our galaxy continues on a couple of other fronts. Just recently, astronomers found that there was another star here that actually breaks the record for the closest approach to this black hole. The star is creatively named S62. All right, that's not very creative, but I've put its orbit here in kind of a lighter orange color, and you may be able to pick out its closest approach to the black hole. For those of you that remember our solar system shows, this star's closest approach to the black hole is at about 17 or 18 astronomical units. That means if we dropped the orbits of the planets here in the center of the galaxy, this star would get a bit closer to this massive black hole than the planet Uranus orbits the sun, which is pretty impressive. Such close approaches to the black hole may actually physically change the star in ways, may stretch it out just a little bit, just because of the intense gravity the star encounters. This can certainly happen for other objects close to the center of the galaxy. In fact, also in the last year or so, astronomers have identified a new kind of object here at the center of the galaxy. These star objects are just given designations that start with the letter S. They found some new objects that seem to be wrapped in clouds of gas. So these are called G objects. I'm putting their orbits up there in blue. And one of them was seen to approach the supermassive black hole and get stretched extremely by the gravity of the black hole itself. And if it were just a plain gas cloud, astronomers figured it would be totally torn apart by the black hole. But as it receded from the black hole, the object seemed to kind of reform, become a more coherent object again. So we aren't really sure what's going on here. Must be some gas involved because the object got really stretched out. But then again, there must be some massive component at its center because it was able to kind of reform as it got farther and farther from the black hole. I'll try and track one down here. I've just kind of modeled them based on the best artist representations that are available here. Maybe it's an old star that still has some of its outer layers bound to the ancient stellar core, but we don't really know. So there's a lot more to learn about the center of our galaxy, and really there's a lot more to learn from all across the galaxy. And it's going to be especially interesting to study objects across the galaxy if we use more than just our own eyes to explore it. After all, radio waves have been incredibly useful in exploring the rest of the Milky Way. So I thought for next year's show is kind of get a little bit closer to an imagined G object here at the center of our galaxy. We explore our galaxy a little bit more, but we're going to ignore objects we can see with our own eyes, or at least ignore their appearance as we would see them if we simply put our eyeball up to a telescope. So we're going to explore the rest of the electromagnetic spectrum and take a look for some, what I have called ghosts in our galaxy. We're going to see some otherwise invisible objects that are only revealed if we study space in wavelengths beyond the visible part of the electromagnetic spectrum. So I hope you are able to join me again next Thursday afternoon, 2 p.m. Eastern Time. We're going to go ghost hunting, and we're going to explore a little more of our galaxy. Until then, certainly go out and try and catch Comet Neowise. Again, for the next couple of days, early morning hours, and cross your fingers that it's still visible next week when it is visible just after the sun sets in the evening. There's also a good time of year for passes by the International Space Station. There's going to be an especially good one here in Richmond next Tuesday night, about 10 p.m. It's going to fly almost directly overhead, so just be outside at 10 p.m. and weather permitting. I dare say you will not be able to miss it, but we can certainly provide more details if you are interested. Just let us know in the comments if you need any more details about any of these topics. And if you have any other questions about anything we saw today, any requests for something you'd like to see in a future show, please leave those in the comments as well. Your input really does help shape these broadcasts. So until next week, when we search for those electromagnetic ghosts in the Milky Way, stay safe out there, enjoy your week, and I hope to see you next Thursday.